Hello and welcome to Knowledge Forest. In this series of videos I'll be deriving some physics formulae, some physics principles. We'll be deriving some physics principles from the ground up. So in this video I'll be deriving the electrostatic potential in a circuit, or basically the electrostatic potential in a circuit of charges or experienced by charges when they are moving. So let us begin by doing this derivation. So let us say that we have the charges in space, right? And there is an electric field that is static. That is to say, the electric field is not time varying, or it's not varying in time. So this is to say we have got the following scenario. We have got some field that is applied in space, right? And this field is an electric field. So let's call it electric field E. Now on our electric field, let's say that we place a charge. So we place a positive charge, Q, right? And this positive charge will experience a force that will move the charge from a point A to a point B due to the electric field. So let us then say that this point charge moves from this point to that other point. We call this point B, we call this point A, which is the beginning point. Okay, so the point charge that is in space, or this charge that we have, the charge Q, experiences a force that pushes it. So let's indicate that force. So then our point charge experiences a force that is in the direction, or in this direction, or rather we can say it's something like that, which makes it go in that direction. So it experiences a force Fe, which is equal to the charge magnitude times the electric field, or the electrostatic potential. This is the first thing we must know. When you're looking at charges that are moving relative or due to a force that is exerted on them, they experience a force QE, and they start moving in the direction that we indicate there. Okay, so now let's say that this charge did move in this direction. However, let's say now it has now moved to this point B, but we decide no, we want that charge to go back to the point A, so we apply an external force. But this external force that we apply is just slightly bigger than the force Fe, which is QE. We just say it is slightly bigger, such that there is no acceleration on the charge. Because we understand that when the force is in that direction and the force in that direction equal, then the net force is equal to 0. But we still want our charge to move, so in other words, we're saying it moves at a constant velocity. So let's say then this charge then moves from the point B back to the point A, but it follows some sort of path, right? And this is still our electric field E. But then our charge now experiences a force in that direction, which is now our external force, or we call it EXT, or XT. So the EXT force, or the external force, is that one which is moving the charge back to that position. So it is now moved from the point B back to the point A. Alright, now we notice something. There is a path going from A to B, and there's a path coming from B to A. So we can say we've got this following scenario, our electric field, right? And the charge moving from there to there and back there. So there's a path it takes when it's going that side, and there's a path it takes when it's going back to that side. So there are two forces, in other words, that we're looking, and it sort of creates some sort of area that is elapsed by this path, or this path of traveling. So this is the force due to the going that side, or back by the external force. So F xt, and this is the force due to the electric field, and let's call it Fe, which is equal to QE. So we've got the following scenarios. Okay, now let us notice something. There is work that is done on that charge, because it is moving a distance, right? Then work is done on that charge. So we understand that the work done due to this force must be that dW should be equals to the force, in this case it is QE, right? Dot producted by the path that it travels, the small path. So let's call it dl. So let's call this a small dl, right? So dot dl. But now due to the external force, because we are saying that the external force, ext, is slightly greater, right? So it's slightly greater, but approximately equal to this one, which is Fe. That means which is equal to QE. So we are saying then that this Q, the external force, or the dW due to the external force is approximately equals to that QE, right, dot dl, but we of course notice that it is in the opposite direction. It's going in that direction. Okay, now having that, we can start thinking about some element or some things that are happening. How do we define the potential? What is the potential? How can we find the potential? But before we get there, let us then say that for this closed path, what is going to that path and back, we have got a closed surface integral. We've got a closed path integral. So let's say we want to integrate the dl, this dw, our work. So we'd say the total work would be something like dw, which is the integral of qe dot dl, right? Something like this. So this is the integral that we have. But of course, let's say then we want to look from A to B, we then have the following thing or the following scenario, that the closed surface integral or the closed integral of the total work that's happening, the total work going from A to B and from B to A would then be the closed surface integral. Before we go to the closed surface integral, let's say from A to B, this was A and it was B. So from A to B, right? That we have it there, and that is going to be QE, right? Let's have QE. QE dot DL, right? That's that work. But then we also have negative, because the other one is in the negative direction. So minus from B to A, B to A, so we've got QE dot GL, which is an approximation though. Then we can then say, of course, this is now an approximation because we included an approximated value, which is something like this. Therefore, we can clearly see that the work, the total work, if it's a closed surface integral, right, from A to B, would then be, so let's call this path, or let's call it, or this whole path that is traveled, let's call it S prime, for example. So the S prime integral would then have to be QE, right? QE dot GL, and this is equal to 0. So there is no, it's actually equal to, because this closed path has got no work. So basically no work has been done because we've got to this position and we came back to the same position. And we know that work is defined as the force per unit length. But then we understand that the distance, or force per unit distance, but we understand that the distance has now become 0. So initially we were saying that the total work is essentially 0 because we are back at the same position. Right? Now we have that, we can clearly see that by this observation, we can take out a Q which is not part of the integration. We then have something like this. Q outside the closed surface integral of E dot GL. So we've got this here, and we understand that we say that this is equal to 0, which is interesting, because now we understand there is another theorem that exists in physics. And this theorem, we call it Stokes, yes, we call it Stokes theorem. Now we see that here we enclosed a path dA, so there was an area that was enclosed. And we can apply Stokes theorem here, because Stokes theorem says that if you've got some function or vector function A dot dl, right, and it's a closed surface integral, this is the same as saying the following, the integral of lambda, or the curl of the function A, which is in this case or that way, and we put it by a unit area, right? So we've got a path which encloses an area. In this case, the path going and the path back encloses an area. We can apply this to our equation there, and we can see that we end up getting that work is then equals to Q, right? And we've got this being the situation dot A D A, with of course a dot product there. But no, not that we are not using an A here, we are actually using the E. But then we understand something again. We say that this was equal to 0, which implies that the integral, the left-hand side must be equal to the right-hand side. This gives us, or this leads us to the conservation of electrical or electric field in a static case, which implies then that the curl of the electric field in a static case must be equal to 0, which is interesting. Because the curl of the electric field in a static case must be equal to 0. And because we've got this result, we can then use Laplace's theorem. And Laplace's theorem says that the Laplacian of the vector function E or V, in this case we want to use V, in this case of the potential, must be equal to 0. Which is very interesting, because here we understand that this will give us, we understand or we already know that the electric field in any situation is actually equal to the negative gradient of the potential. So because of that electric field conservation, this implies then that E should give us the negative gradient of V. That should be the case. So that we have that is the case, which implies that we can then start using this one at some point, or it will give us a lead, or it will lead us to this law that we want to derive, which is the potential of this vector field. Okay, but before we go there, we have another identity that we know, or that we can start using, or that we can think about. But before we do that, let us try to put in or substitute in the electric field with respect to the potential. But you want to put it there. So this is the electric field. Let's put it back into this equation that we had. We then have the following. So let us put some space there. We have that the work then becomes Q, this multiplied by that, which is the negative gradient, right? Negative gradient dot dl. But we have a vector, we have an identity which exists in physics. And this gradient says the following. If you have df or df, the gradient of a scalar function, or the gradient of any scalar function, right, is actually equals to the, in this case, the nabla, or the curl, or the gradient of the scalar function itself, dot producted by the dl, or the product by dl. This is a standard identity which exists in physics. It can prove that this is the case. So since we have that identity, we can use it. Let us use it for this case here. Then we can then see that the following becomes work is equals to Q, right? And the closed surface integral, which is this, right? Of now our dV, right? Which we now have a new form here that we can think of. But let us then say no. We only want to consider the force or the work that is done by our external force. Back to our diagram here. We are now interested only within the work that is done between B and A, coming from B to A. So even though that is a closed surface integral and it is initially or actually equal to 0, we don't want the closed surface integral. We want to excite ourselves, or want to think of ourselves referring only to the integral that happens between A and B. In other words, we are looking at the vector or the potential at V equals to A and V at B. So we are then going to have the following case, that we have got that the work done from B to A is actually equals to Q, right? And of course it is an integral that we have here. And of course we had a negative, yes, we had a negative outside. But of course the negative does cancel out, because the moment you're looking at dV, the change, there's a negativity that's coming. Because here, the potential here, the potential there, both directions were involved. Now we're coming from this point back to that point, so we can say the negative cancel. But before we put it in there, let us just put in a bounds, which becomes V at B, V at B, V at B minus V at A, dV. This then gives us the work. Only just use the work, A, B, or B, A, right? So we're going to say now from this point onwards, W, the work is now representing the work from B to A, which then actually then becomes simply just the work at B, or Q, the potential at A minus the potential at B. But then let us say no, let's just put it as one value instead of having two values. Let's just say, let's define a change in volume, or rather let's define the VAB. So now let's say VBA or VAB, because we're coming from the potential at A to B, so VAB. So VAB is actually then going to be VA minus VB. In other words, the potential at A minus the potential of B at B is equal to the potential AB. Because of this, we can then see clearly that then the work is going to be equal to Q VAB. Q VAB. And as a result from this, we can make V the subject of the formula. Then we end up having simply that the potential at AB must be equal to the work done on the charges per unit charge, right? So we initially find, then we find that the potential difference is actually the work done at the point, or the work done between A and B is actually equal to the work done per unit charge. So the work done on the charge is per unit charge, or the work done per unit charge. That's essentially what the vector potential is. So the potential difference, or the force that causes the charges to move, it is the work you do on them per unit charge. So that is the definition of the potential difference. But we can also clearly see something that since even though that we got this position, we can notice something then that this is the same thing. Okay, let's just put in the AB for the sake of clarity so that we don't get lost. So BA and BA, or AB, or this is actually AB. So let's put it as AB, and let's say AB. So this is actually what it is. So V, the potential of AB was work done from A to B between at the point of per unit charge, which is Q. So that is the definition of the work, the vector or the potential difference, which is the electrostatic potential difference. And all this is happening within an electric field that is static. In other words, it's not time varying. But from this derivation, we find something important. The electric field does not rotate. The electric field does not rotate in a static case. That is to say, when the electric field is time invariant, it does not rotate. And as a result, we've got the conservation of the electric field. From that, which enabled us to then think of using this formula, which is then giving us that electric field is actually equal to the negative gradient of the potential difference. Of course, this is when we are starting looking at Laplace's equation. Because there is no volume charge density, there's no volume charge, it's only one charge we're looking at, so there's no volume charge density, and we can use Laplace's equation. But this is already thinking too far. What's important is that we managed to come to that conclusion about the vector potential from the derivation of that area and involving Stokes' theorem in order to get to this point. So, now having that in the mind, we can then think about going on to the next version or the next part. So, let us see something. Allow me to put you to this board here, which is closer there. All right. So now let us say then that no, even though that is the case, we find out indeed that indeed the work done from A to B is indeed equals to Q, V, A, B. We understand that is the case. But then we want to see what is it. We want to express this one in terms of electric field. We want to express the potential difference in terms of electric field. We notice something that if we say let the potential difference be positive, let it be some positive value, in other words, it's not equal to 0. So if the potential difference is actually a positive value, that is to say, if WAB is a positive value, this should imply that the potential difference at A and the potential difference can be indicated by some inequality. And this inequality simply says that the potential difference at A must be the greater potential than at B. Okay, having that, it means that the external force that is acting on E is increasing with time. So the external force that is acting on the charge in the field E is actually increasing. In other words, the negative then should appear, right? So then we end up having the following, that VAB. Let us now say no. We want the electrostatic potential difference only at A. We don't care about B. We want it at one single position. So how then do we do that? We say that in the limit that B or the point B gets very far away, in that limit we are going to get something exciting which happens. And this becomes that we are also saying that B is gone very far away, but also at the same time we're saying the charge is on, or the charge, so the amount of charge is approaching 0. So this becomes the limit that the charge, right, is going to 0. So it's becoming it's becoming a point, it's looking like a point from the point B. So the charge at the point A or the charge at any position is not looking like a point. In other words, there's a difference in direction or in distance between the 2 points, right? That in the limit that Q does go to 0, of course, our work here, AB per unit Q, there should be something that must happen there which is very interesting. But now let us put in back the equation for WAB, which we understand we've derived it there to be E dot dl. So this should then become, of course, there was a negative, because now we're going in the negative direction, because now we're saying A is bigger and B is getting very far away, so to go back is becoming very slow. So it then becomes then the following, negative, let's say 1 over q, let's use it as 1 over q, and of course the integral, right, E dot dl. So we are saying that q is approaching 0, or is becoming a very small value. Or now let us remove this, because this will give us a 0, so we don't want to work with a 0. So let's just say from B back to A, but approaching that B is now becoming some point that's going very far, or it's becoming an infinity value, or a value at some point which is a bit far. We then see the following, that we can do this right here, which becomes the following then, the following case. The limit, I don't know why I removed the limit, so let me put the limit back here. That q approaches 0, right? The limit that q approaches 0 is then the integral from B to A E dot dl over q, right? We've got, this is the case. All right, but then we also do see something that is very important. The potential difference itself was already defined with having a q inside. There, when we define the potential difference, it already had its own q. But then when we put this VB, where that the work was over another q. So we end up having a q which is outside, right, and the q which is in the inside. So we are saying that these charges are approaching 0, so they cancel out each other. So we end up just simply having the integral E dot dl. So VAB then simply becomes the integral from B to A, and it's E dot dl. So let me re-explain exactly what happened. It seems like a little bit of a fishy case. We're saying that we want to look at the potential difference, though here we're saying that we are looking at it from the points, between the points A and B. But between the points A and B, one charge is becoming very slow. That Q is becoming a very slow charge, a very small number. Therefore, as a result, this Q, since we said that the work done itself here, WAB, we already defined it to be, WAB was already defined to be the integral with a Q, of course, outside between BA and it was E dot dl with the negative outside, I believe. Right? That being the case, that negative should still be in the negative. We put this Q over Q, then these Q's become 1Q, a charge on top and a charge at the bottom, and these cancel out because they are approaching 0 anyway, so they are points which are necessarily or almost negligible. So then this becomes the electric field, or the potential difference at the points A and B, or between the points A and B, that is now independent of the charge. It is caused, of course, by the electric field, but it is independent of the charge, because now the charge is out of the question. So you can then say, if you were to place a point charge between the points A and B, what electric field what potential difference will it experience? And that potential difference is exactly this one. And the negative implies that the potential difference is in the direction opposite to the direction of the electric field itself. And this right here, ladies and gentlemen, is the derivation for the electrostatic potential in a static case, whereby the electric field is time invariant, and this is how we get to derive it, and that is the conclusion, hence this derivation. So, I hope this was helpful. Thank you.